So we will start, or I will start with a brief introduction on data visualization. It was very difficult for me to think about what I will present today, because as you know, this year's course structure looks slightly different than usually, or than before at least. And it's always difficult to think about what could be more important. Are we talking about general aspects of visualization, or are we talking about specific aspects that are important if we build monitoring reports, if we build monitoring dashboards, for example? I tried to prepare a little bit of both. In this short introduction, I will mainly go through some basic principles, which also are already very relevant for everything of data visualization in a research context. So things that are relevant if you prepare your thesis and the end of this master's program, or also if you prepare research studies, for example. Some of these things could be directly related or transferred to monitoring aspects from my experience and from the things that I observed from other practitioners. But I think not all of these aspects are commonly applied for different reasons, because if you prepare just one important figure for your main outcome of your research study, you would always create this differently to communicate information to other researchers, compared to you have lots and lots of data which you want to present to an athlete, to a coach, to another practitioner to make a decision in sports practice. So just the way of looking at data, the amount of data, the way, and basically it's a way of communication. So the way of communication, the aim of communication is typically a different one in monitoring settings. So you will see some things that I personally would not directly transfer to monitoring setting, but that I would refer to, or that I would transfer to research context. And yeah, we will see how it goes, and if you have questions afterwards. And we also try to apply the things that I talk about in the next minutes to the things that we saw last week and the things that I did, and the examples of visualization that I want to show you. 2 points, mainly talking about some basics of visualization, and then giving 1 or 2 examples, also where we work in Excel, where we recap on what we just heard and try to apply the things to the things we saw last week's in Excel. So almost everything I show you in the next slides, except the last slide, is directly copy and pasted from this book. This is a very great book on the fundamentals of data visualization from Klaus Wilke, who was interestingly educated and who did his PhD in Bochum at Ruhr University. Now he's, I think, theoretical physics or something like this. He has written this great book, which is very, very useful. And the amazing thing is this entire book is openly available, open access available. So all the figures can be used for everything you want. Basically, the links are as usually displayed in the presentation on the right-hand side, or just by clicking at the links. So everything you can see is also as a 100% open access book online. And I highly recommend for everyone who wants to recap on some of the things I present you, look at this book. It's just amazing, amazing examples, many amazing thought process. And this is how research and teaching could look like if everyone would think about what is most useful for our society and not just for the publishers. But that's a different problem. There will be different examples where the author, Wilke, showed or tried to focus on different aspects, which kind of ways of data visualization probably look ugly. Ugly means that the figure just has some aesthetic problems, but in general, the information is presented clearly and informative. For example, figure B. There are versions that are bad because, as you can see, we have different axes for all the different categories. Just is basically problematic in relation to perception, because we would assume the way we see the height of the bars has a specific meaning, but we then need to consider the different axes at the same time. So it just makes it very difficult to compare the different categories. So this is a very bad choice for visualizing data. And they're also more or less objectively wrong ways of visualizing the data, because here we have the same data as in the other figures, but we don't see any axes. And it just appears that the differences are larger and that the relationships between the categories are differently, because the y-axis basically starts at 2 and not at 0, but we don't have any information about where the axes start, the y-axis. So therefore, this way of visualization is probably wrong, and you will see these indications of ugly, bad. I'm not sure if I have an example for wrong also in the next figures. And the basic idea is, okay, we always have to make some decisions. We have to take some choices about what we want to visualize and how we do this. And depending on who you ask, there will be different interpretations of ugly and bad. But I want to focus on some things that could be suboptimal depending on the question you try to answer. And this is what the next slides will be about. Let's start. So for example, we have different types of figures that are typically useful when we present or when we try to visualize different amounts. Most commonly, if we think about, for example, how much income does someone has, how high was the heart rate, how much distance did someone run in a specific intensity zone or whatever. It's very, very common to use bar graphs, different kind of bar graphs, vertically or horizontally displayed, sometimes also dot plots. If we have multiple categories, we could use grouped bars, for example, or stacked bars. And in some situations, there are also heat maps useful for presenting amounts. It's also very common to look at distributions, mainly in respect to histograms, for example, if we're thinking about frequencies. Or we can think of density plots, which show the distribution slightly more nicely, I believe. And what are probably relevant to us is also looking at distributions of data in types of box plots or some kind of data visualizations, for example, strip charts or scatter plots. There are also the possibilities to look at stacked histograms or overlapping densities, for example, and some examples will be presented there. Like if we are interested on where the data lays in our one or two populations, it might be useful to think about histograms or density plots in many cases, or if we have different categories, also different way of more or less dot plots where the data is displayed in some kind of spread is also very useful. Proportions, the typical one is pie chart, which is probably one of the most problematic ones, multiple pie charts. What is often more informative probably is different ways of bar charts or group bar charts, for example. The other ways are more relevant for different ways of research, and we don't focus on this today, but mainly looking at proportions, the difficulties with pie charts and opportunities with bar charts. If we want to display relationships between two variables or more, it's very common to look at scatter plots, for example. This is the one way of visualization. It's most common in our research field. Everything else is most of the time more related to more complex data. And what is also very important, if we think about measurement error, if we think about statistics, also again, more a little bit on the research perspective, but we can also apply statistics in monitoring context or when working with individuals. Uncertainty is a very important aspect. So uncertainty in our estimates, uncertainty in our statistics, basically. And the most common way is to display uncertainty in terms of error bars. If we have mean values, for example, and we show the uncertainty in terms of an error bar around this, we can plot error bars on dots, on bars. We can plot error bars in both directions if we have two variables, for example. We can show different ways of confidence intervals, for example, or we could use different ways of displaying distribution. And uncertainty can also be displayed in different curve fits, for example. So where the error bars mainly are drawn for each possible point over the entire spectrum, and therefore a shaded area basically is displayed, which displays the confidence on the different levels of possible values. Looking at the first examples and take some time to look at these two different ways of visualizing amounts. So in this case, how much weekend gross was there for the different movies in the cinema. And on the right-hand side, you can see, for example, one probably more ugly choice, but of course, ugly is always a very subjective term. But what is suboptimal on the right-hand side is that the labels are flipped, the labels are rotated. And yes, it's a little bit more efficient use of the space that we have for the figure, but it's far more difficult to read the labels. On the left-hand side, looking at the labels for the different films, for the different movies is way more easy than on the right-hand side. So always think about, does the client, the athlete, has to read the things that are displayed on the axis? And if this is the case, if the labels are very important, the right side is probably a very bad choice, because it just is more cognitive load to be able to read this, or you have to put your head around, and just doesn't make sense too much. If we want to go around this, we could, for example, decide, as you can see on the left-hand side again, displaying horizontal bar plots, and it's far more easy to read the labels of the video, or the labels of the movies, I'm sorry, and also to read the important x-axis in this case. So what are the values that are actually displayed? Once again, we go back. The y-axis, if we have the typical labels in a vertical way, it's always, again, a little bit more difficult to read what is actually displayed here. And if we flip this to a horizontal bar plot, all the information is more easy to access. Another bad choice in this case, because we want to show some kind of order, which movie has the highest weekend gross and what is the order of the different weekend grosses for different movies, for example. And if we only look at the right-hand side, and we have some order of the longest name of the movie to the shortest name of the movie, the main information, what is the weekend gross, is very badly displayed, and it's difficult to understand the main order, which movie has the highest value and which has the lowest value. So if there is a very clear structure, if there's a very clear order in the information that you display, order the values. All right, don't think about the labels, order them by magnitude. It's also very common to look, for example, at things like this. So this could be several aspects also related to monitoring practice, which I will come to an example in a second. But here you can see the mean income for different age groups. And as you can see on the left-hand side, there's the distribution displayed more or less in bar plots. What's the mean income for different age groups? And we can directly see the effect of age basically on the mean income, which is quite clear. If we then take the principle from before and order the values by magnitude, the information on the age, as you can see here, is lost immediately. So basically ordering, in this case, by the amount of mean income is probably a very bad choice, because then it's almost impossible to see the effect of different age groups. So in this case, this would probably be a very bad choice if we wanted to show the different incomes over the age groups. Always think about the message that you want to display, or the message that you try to get across, and if it makes sense to order your values or not. An alternative is, if we look at mean income, and for example, we have different categories. So for example, in the upper figure, we have also the category age, basically, and we have category of race or ethnicity. And here, each ethnicity is displayed in a different figure. We can see the overall distributions mainly, but what's probably a little bit more efficient way in many questions or in many situations is, for example, my understanding, or at least from my understanding, the lower figure. So where you can see, for example, the distribution over age for each ethnicity, which makes it very easy to see the effect of the different ethnicities and ages, for example. In the upper figure, it's very difficult to see, okay, for the Asian ethnicity, what is the mean income over age? Okay, I need to look at the dark blue areas. For the black population, I need to look at the very light gray areas. It's difficult to see the distribution of the different categories and compare the distribution because the information is just mixed. I believe the lower figure is way more informative for this, because you can see there's a very clear difference in the overall incomes for the different ethnicities here in this figure. And you can see at the same time the effects with age. So just by ordering the grouped bars in a different way, the information is way more clear. And in the upper figure, it's probably only a good decision to display the figures like this if you are directly interested in looking at the effects of ethnicity in each specific age group separately. But many other informations would probably be better displayed in the lower figure. An alternative way is that you can also, for example, separate the information in basically split plots, where you get rid of the different color shadings and you have the information on the age directly displayed at the x-axis in addition. So for example, by using the same y-axis for all the different part figures or split figures, basically, you can see, all right, Asian still has the highest income overall, and we see the different distributions for different age groups. We directly can see the age groups without needing to refer to a legend and the different color shadings. And again, by looking at or by using the same y-axis with all the four figures, it's very easy to see the overall differences between ethnicities. All right, so an alternative way to displaying everything in one figure using four smaller figures, for example. This could also in some cases be a very informative way. And this could be, for example, also being time spent in different heart rate zones, time spent or distance spent in different running zones, for example, for different playing groups. So for example, we have the forwards, we have the back, we have the forwards, we have the centers in basketball, and we have the shooting guards, for example, or whatever. So you can have different categories and display the distribution of different variables quite effectively, if you want to look at this. Another alternative is sometimes visualizing amounts in types of dot plots. We can see here in the dot plots, also very effective to order the different countries by life expectancy. If we use bar graphs in this situation, and we also start the x-axis at 0, we probably waste lots of ink for very little amount of information. And in this case, for example, it appears that countries basically have quite similar life expectancy because the difference between countries is very small. But if we look at the left-hand figure, and this is probably the more informative thing because average life expectancy is never lower than 60 years, it's probably better to cut the y-axis for the information or for the range where all the information is displayed. And therefore, looking from left to right, it's probably a better choice in this case to display amounts in terms of dot plots and get rid of all the color on the right-hand side, which is probably just a waste of space and a waste of ink or digital ink, basically. Again, a very bad choice would be to order the countries by alphabetical order, because all the main information that is relevant is not possible to extract. It's very difficult to see, for example, United States, which line is it, which life expectancy does it have, and compared to Mexico, for example. So using ordered dots in this case would probably be the choice we should make. If we think about distributions and looking at frequencies, for example, this is very common for statistics, for example. We very often have histograms to display a distribution of a different variable, but we have to be aware, depending on the bin width, like the width of the bars that we look at, the data can look very differently. Same thing for density plots. We can also use density plots instead of histograms, for example. If we decide on different kernels or bandwidth, data on distributions will look differently. So yes, it is a good choice to visualize distributions in terms of histograms or density plots, but depending on the selections of the parameters to visualize this, the distributions could look differently. And this is what we have to be aware of. Another thing that is very important from my point of view, because we see this quite often in sports research, for example, and I also showed some figures in the past that look like this, where we try to visualize different types of distributions by stacked histograms. So we can see in the left-hand side, for example, that the male persons, the distribution of the male persons for the different age groups is quite nicely visualized. But if we then put all the female persons on top of this, it's very difficult to understand the distribution of the females. We do see what the overall distribution is, but it's almost impossible to understand what is actually the distribution for the females. For example, is this age group different to this age group? An alternative way could be to have overlapping histograms, for example. But in this case, the overlapping histograms would probably also be not effective, because although we only have 2 categories, it appears that we have 3 different types of figures. Sorry, 3 different types of colors, and therefore it's not perfectly visual clear which kind of distributions do we have. Is this another color, or is this just basically the blue color in the background? Alternatives would be, for example, looking at overlapping distributions, which is far more clear from my perspective. We could also think about displaying the different distributions in relation to the overall distribution. And then we can see, okay, there were more males than females from left to right, and the amount in different age groups is also very clear compared to all passengers, in this case to the entire population, for example. So this is probably a better way of displaying multiple distributions. Also, what we see quite often when looking at ages is, for example, this way of visualization, which also makes it very clear that the overall pattern of females and males of the distribution looks quite similar, but we have way more males. Also, different choices which are probably more efficient to display this information compared to stacked histograms or overlapping histograms. All right. Proportions, also very common. The typical way of looking at this is in terms of pie charts. But as you can see in the upper figure, I believe it gets clear quite easily why this is most likely a very bad choice. Because we do see that the pie charts are not exactly the same between years, but it's extremely difficult and extremely hard to understand which of the 5 categories, which of the different companies changed their values over time. Another way of displaying this, and this is also very common in sports research, when we look at training distributions in different intensity zones, for example, over different years, is to look at relative, look at stacked bar charts, which always add up to 100%. So in this case, yes, we do get maybe a rough understanding of how the companies relate to each other, but we can probably only see the trend over time for different companies, only for category A, for the orange ones, for the orange company, and for category E for the yellow company. It's very difficult to see, is there a difference between the category C and the green ones over time, or is there not? Same thing with the pie charts. It's almost impossible to see, are there any differences, and if there are differences, how large are the differences, and how large are the differences compared to the other companies. So in this case, for example, looking at the proportions, which all add up to 100%, for example, then it's probably, again, way more effective to use side-by-side bars. Then we can see, for example, the trend over the weeks for different companies. We can see the order for different companies, and it's way more easy to understand the differences and the effects over time. So I believe, and I always struggled with this in the past, but maybe there are also some personal preferences. I always struggle to look at proportions in respect to pie charts or in respect to stacked bar charts. So making side-by-side bars is probably way more efficient. And this is very important because this is what we deal with quite a lot, is visualizing time series. We're having data over time for different individuals or for different teams or something like this, and we're visualizing data over time for one variable, for example, or multiple variables. Quite common is, for example, to either look at dot plots, but probably, again, a better choice is to connect the different dot plots because we're looking at time, and we know that the first data point to the second data point is related to each other. They are basically dependent variables, and if we're looking at dependent variables, if we're looking at changes over time, we most oftenly use also lines between dots. This is quite an effective way to look at the trend over time, basically. You can also think of getting rid of the observations, getting rid of the dots, basically, and only displaying the lines. This makes the overall trend a little bit, or this puts the overall trend a little bit better into the focus, and it gets rid of the focus of the information of the individual observation. This is probably a matter of choice if you also want to be able to display the individual data points, or if you only want to visualize the overall trend over time, for example. But looking at trend over time, most often it's a good choice to think about line graphs, for example, or different types of line graphs with or without plots. Again, a poor choice if we're thinking about only looking at dots over time. If we have multiple categories, it's very difficult to look at the trends over time and look at the differences over time. So yet again, if we use line graphs instead of only dots over time, it's far more easy to understand the differences. And again, if we only want to focus on the trends, we can also get rid of the dots. But time series are typically displayed as lines and or connected dots. A final thing, which is probably more relevant to the research setting, but we also face this if we're thinking about measurement error, for example, is visualization of uncertainty. And in this case, you can see different ways of uncertainty in point estimates. So point estimate could be, for example, an average value or mean value. The typical thing that we need to understand is if we use error bars, as in this case, to visualize variability or uncertainty, is that error bars can mean different things. And the basic idea is if I'm interested in an average of a population, you can see the population here, for example, and the standard deviation displayed up there. If we take a sample, and if we take a sample of a mean and we calculate the standard deviation of the mean, we could also display it like this. But we have to be aware if we're talking about uncertainty, uncertainty is related to a sampling distribution of means and not about the distribution of the raw data. Like error bars, uncertainty is mainly related to statistics, and statistics are about sampling distributions. And therefore, an error bar, which is displaying standard deviation, obviously is way larger and has a different meaning than an error bar, which is displaying a standard error, for example. And you always have to make sure, and you always have to present what is displayed, are you displaying standard deviation or a standard error. We won't go too much more into the details of what is the difference between standard deviation and standard error and what is sampling distribution. This is something for the statistics courses, but this is very important because, and this is why I also want to show a couple of more examples. So for example, in the upper figure, we have a different sample. The dots display a different sample. We have here the big red dot is the average of the entire sample. Looking at the spread of the data, the visualization of the standard deviation would look like this, so very large variability between data points. But because we have a quite high sample, the standard error is of course way slower, But because we have a relatively high sample, the standard error is way smaller than the standard deviation. And so therefore, if we're displaying error bars, we need to know, are we displaying standard deviations or are we displaying standard errors? And of course, we can also display different confidence levels. And confidence levels are always related to standard error and not standard deviation. And depending on the width of the confidence interval, it gets some different information of what is the actual confidence interval. If we are interested in showing uncertainty in ways like this, there's also the opportunity to show different ways of confidence intervals. So for example, 80% confidence interval, the 95% confidence interval, and the 99% confidence interval at the same time, for example. So we can use different colored and different width of error bars at the same time to show different types of confidence, for example, at the same dot. Alternative ways, and in the second row, just looking at error bars is probably most common in sports science and sports research, but more and more present is also the different levels of confidence displayed at the same time, either with caps or without caps. And we can also visualize the distributions more differentiated and not like clear cutoff values, basically, by using confidence stripes or confidence distributions. So visualization of uncertainty, either with error bars or looking at some type of stripes or distributions, probably a very effective way. And this gets important for the applied example for monitoring. I know this is very lot, but please keep this a little bit in mind. This is also possible when we look at relationships, when we look at curve fits, for example, either with an individual or at a group level. So we have different variables. We want to relate them to another. We build a linear relationship between them, for example, linear relationship, and we can display the confidence interval, basically the uncertainty around the estimates in a shaded area. And yet again, we can also display different ways of confidence levels, for example, by using different color codings, different way of shadings. This is also very possible for looking at curve fits. This can also be applied for looking at trends over time. This is totally possible. Almost the end, some very important aspects are always related to the coding and using legends and using different types of visualizations. So in this case, you can see a very bad example of displaying the data between two variables from 3 different categories. And the difficult thing is, it's very, very difficult to display the blue color and the green color, and all the different data points, all different groups use circles. And it's probably way more, use circles. And it's very difficult to see the difference between the distributions of categories, green and blue, basically. And what we always have to keep in mind is, and there are probably also some persons in this class, that we have different ways of visual limitations, basically, of different types of blindness, for example. So depending on your limitations in the visual system, it could be extremely difficult to separate different colors. So in the past, there was also a great tendency to only look or to only use black and white, but only using black and white or gray shadings can also be difficult. So colors do have an important point in data visualization because it can help bring the message across, but you always need to consider different ways of limitations in visual aspects. So for example, there's possibilities to simulate different types of color blindness, as I say, for example, and you can see that's very difficult for many types of color blindness to be able to get the different informations out of this figure. How can we deal with this? Is that we use redundant coding. So for example, on the right-hand side, you can see a probably very efficient way of visualizing the data. We use for the different categories, different symbols. So we have circles, we have squares, and we have rotated squares, basically. We use different colors. We also show the typical range of data distribution by showing eclipses, for example, for the different categories. So it's very easy to separate the distribution and the data points from different categories. And we directly use not a legend, but the labels of the different categories right next to the area of the typical distribution of the data points. So we use different ways of coding the different categories by just making it easier to get the information across. So either I'm looking at the colors, or I'm looking at the figures, or I'm looking at the shapes of the main area. All these informations help me to understand the main information. We are looking at different categories and we want to see how different are the different categories. All right, so redundant coding can be a very effective strategy to bring the message across to the ones who are looking at the figures. Tables, only very briefly, upper ones are displayed as ugly because probably also personal choices. So it's always recommended to use as less or as little lines as possible, which is a very scientific way on the left-hand side. But on the right-hand side, especially if we have lots of columns, it can be very effective to use different shadings for different rows to make it easy to see which data relates to which row. Especially if we have lots of columns, it can be difficult to only use example C, because then it's always difficult to see, okay, which was pitch perfect 3 and rank and the rank on the film with the third rank, and so on and so forth. So probably look at data visualizations for tables in respect to examples C and D. The upper ones are just very difficult to focus on But of course, lots of personal choices there. Final thing is, it also is helpful to provide some context. So the grid lines can be very effective. So the horizontal and the vertical and horizontal grid lines can be helpful to understand what is the differences between the different data points, but this is probably overloaded on the left-hand side. On the right-hand side, the main information is probably clear enough. You can see the differences in height by 10 centimeters, which is probably quite good accuracy for this, and also differences in body fat of 5%. So for example, we can discuss about how many grid lines do we need to display the different informations, but it's very helpful to think about what is the appropriate amount of context. Here on the left-hand side, probably too much lines, which makes it a little bit more difficult to focus on the important aspects. On the right-hand side, there's probably a better amount of context to still be able to interpret individual data points. Final aspect is we need to think about the balance between data and context. So for example, yes, we do have a lot of context with the grid lines in the upper figure, in the left upper figure, but there's probably lots of ink that is irrelevant, so maybe not a too attractive option to display the data. In the lower point, it's very difficult to see, okay, which values are we looking at this point of the graph compared to this point of the graph. So we don't have a good understanding of what the actual trend looks over time, how large the trend is. So it can be very effective to look for or to display, for example, at least the reference value, the starting value of 100% in this case, which can be very effective to see, okay, all the different companies have values that are very clearly above the original starting point. Or we could again think about, because this is the main information here, displaying only the horizontal grid lines to see, okay, this is a difference of 100%, for example, in stock price. And, or I'm not sure if it's percent, but in 100 units, for example. And this is probably way more informative when looking at data in context. Sorry, last but not least, it's also very important if you display legends, if you display labels, for example, if you display axes, that the axes can be read appropriately. So on the left-hand side, again, probably a bad way of displaying information, or at least a poor choice of the size of the font. You always, on the right-hand side, probably a better option of looking at this. You always have to think about how large does the text have to be, how large does the figures have to be able to communicate the main information more appropriately. Because you have to be aware, even in this presentation, where we show a couple of images without any text or something like this, this is a very uncommon situation. And even in this kind of presentation where you look at your screens, it's probably quite difficult to get the information. What is the y-axis, what is the x-axis, what are the values, what is the legends on the left-hand side. But you always have to think about figures are typically used in a different context. So for example, in a monitoring report, we typically have lots of figures on the screen. Sometimes we print it out on a one-pager, for example. Sometimes visualizations are displayed on a tablet, on a smartphone. So therefore, most of the time, the figures that we create will be scaled down. And it's very important, if we scale the figure down, if we have the figure in a smaller display, it still has to be possible to get the main information out of this. And so it's also very useful to use large text, large figures, large images, if it's not overloaded, and to still be able to read this on a smaller screen, for example. So the right-hand figure is very surely also being able to quite clearly read on a smartphone screen, for example. And so you have to think about using large and the appropriate amount of axis labels and also of images. So the size of the image, for example, the size of the, how's this called? The size of the plots, the size of the dots, for example, the triangles, the squares, the circles, and so on and so forth. All right, so this should be it for the moment for the introduction. I know this is quite a lot and it's definitely overloaded, But as I said before, everything is also displayed in the book, and there's always examples. There are always small text passages which explain the different choices of the author, and which explain why is one choice probably preferred over another, and so on and so forth. So if it's interesting to you, I highly recommend that you also take a look at this book, just if you're interested in some kind of visualization. But I think at least we had the choice to focus on some different aspects which are relevant, looking at access, looking at the display of the text, looking at the size of the figures and the size of the images in the figure. And yes, this example you also saw before in session, I don't know, 8 or 9, basically. So this is not a good way of visualizing data for a client, but it's a visualization of showing different ways that we could use, or different concepts that we could use to make a decision, and different ways of visualization that we could use where we then only look for 1 or 2 options, for example. So this is not how I would create a graph. This is a graph where I showed different concepts and to illustrate the different concepts, and not a visualization for how figure should be displayed. But this is my common example, and you saw this example in general more often, and this specific example also once before, where we looked at heart rate data in a submaximal test from one athlete over a period of a season, basically. The points represent the individual data from the given days. The error bars represent the typical error, basically, of this test. So we did a reliability assessment in the beginning, or I looked at the reliability values from the literature, I'm not exactly sure. And then the error bars displays basically the uncertainty in our estimate in this test. So the basic idea is everywhere within the error bars around the observed score, the measurement could also lie. So it's also possible on this day that the data could be, that the heart rate, the submaximal heart rate could be here or here, and so on and so forth. So the uncertainty in the measurement is displayed in a typical error, in the error bar, basically, with all the different measures. What we also see is, in this case, for example, a reference range, the smallest worthwhile change, or a meaningful change that is again defined from the literature, which was 1% for submaximal heart rate, for example. And this is displayed as a horizontal bar. So here, there are 2 concepts. We first of all visualize the concept of uncertainty in a measurement by displaying error bars to also communicate to a coach or client, or at least to researchers, okay, yes, this was the observation, this was the heart rate that I calculated. I think it was 173 beats per minute. But I know that I don't have a perfect test, and the values could also range in an entire spectrum. And I visualize a reference. This is the reference from the beginning of the season. This is the level where the athlete started, plus minus a meaningful change. So all changes that are within this reference range are definitely trivial, and only changes that fall outside of this reference range could be interpreted as meaningful difference compared to the beginning of the season. All right, that's the basic idea. And we can then, for example, use visualization. So for example, this point is outside the smallest worthwhile change, outside the meaningful change area, the horizontal bar. So therefore, this observed score is meaningful, but within the error range, it could still be within the trivial range. And you can see here, for example, data like an additional square around the observed score, where the change was large enough that even with consideration of uncertainty, we have definitely a clear reduction in exercise heart rate larger than the meaningful change in this measurement compared to pre-season testing. Right? So all the values that are displayed with another circle around the measurement, a black circle around the measurement, basically display, yes, we have a difference that is larger than the smallest worthwhile change and larger than the typical error, and therefore values that are that have an extra circle are probably quite likely that are actually meaningfully different compared to baseline values. So this is one way of looking at reference values and also displaying uncertainty. We could use this in monitoring practice, but of course we would not also add this table below. We would not use all this different information. We would not use these different labels down here because it's just too much information in one figure. But another way of looking at different ways of making a decision basically is we can also try to use different reference ranges based on individual distribution. And we talked about different distributions also before. So for example, I can look at the entire data of the season and just display a typical range of variability with the two horizontal lines from the entire season. And then I can say, okay, in the beginning of the season, the values were higher than my normal variability within the season. Here, the values were lower than my normal variability within the season. Or for example, the dotted lines represent a normal variability range that creates over time. So in the beginning, I only have 2 to 3 to 4 data points, and therefore the variability in the beginning is only in this area. And the more values I have, the lower the variability, the lower the original values get. Also, the reference range changes over time. So I could be able to display, or I am able to display different reference ranges depending on how I want to interpret the data by using lines, referent lines, by using shaded areas. I would be able to display uncertainty or measurement error with error bars, for example. And these are two examples that are more or less common in sports practice also, or in monitoring practice, how we could put extra information which helps us make sense of the data. Right? And the very important thing is we need to make a decision, and this is what we talked about a couple of sessions ago. We need to make a decision on when would we say this is a meaningful change for my athlete. And it's very useful to think about, am I looking for meaningful change, for small change as a criterion, for yes or no, this is a reduction, this is no reduction? Am I looking for changes larger than a typical error? Am I looking for changes that are larger than the typical error and the smallest worthwhile change? And depending on which thresholds I set for making an important decision, the times I will take a decision would differ quite substantially. All right. And if I decide on one or another approach of how I want to make a decision, I could use this approach to visualize it within my reports, basically.